Yeah, here we go. So it's Wednesday, April 17th, 2024, and I'm talking to Monica Anderson.
Hello, I'm pleased to be here.
Thanks for being on, Monica. So I regard you as the person who really built my intuition about what this revolution was going to be like. And when I moved back to Phoenix, I'm like, okay, people need the same education I got. I kind of stammer around and I can say a few things, but in the end, you can drive it all the way to the math. And so when I talked to you about this, you're like, here's a pile of things we could talk about. And the thing that stuck out is why AI works. And I hope that you'll walk the audience through exactly the same kind of thing that you walked me through. And I haven't heard all of your updates to these things. That's it, Monica. Other than that, I expect to listen. So do you want to give a quick intro on your background and some of your other, point to some of your other work?
Certainly. I'm born in Sweden. I immigrated to the United States in 1982. I have a master's degree from Linköping University in Sweden. I've been interested in AI ever since college. So I have decades of experience, industrial experience with AI, industrial grade AI, as I call it, for decades. And then I have, on top of that, I have 20 years of research into the modern kind of AI. So there was a change in AI roughly around the shift from the 20th to the 21st century. And the sad thing is that nobody really noticed how big a shift it was. And that's basically has been my mission, if you will, for the past decade and a half, 20 years almost, to basically educate the world about what a big difference it is and how it sets everything we know about a whole lot of things into question, including the value of science as a whole. There are so many people struggling with various aspects of AI, which to them is completely mysterious. And it can be even more mysterious to people who have a solid mathematical, physical, scientific background and education. They are the ones that can be the most confused. This confusion leads to cognitive dissonance. It leads to many poor decisions and mean focusing on the wrong things. And it means spending billions of dollars in the wrong places when you're trying to create an AI. And I basically, because of my experience with the old kind of AI in the 20th century, among other things, I had the pleasure of playing with the Psych system, which is the largest AI system of the 20th century for a while. And me playing with it for about 5 hours in 1998 convinced me that it was not the path to go to artificial intelligence. And so I was desolate for a year or so, and then I discovered there was an alternative path, thanks to my friend Ted Keller, who gave a talk about it at the conference. And I basically decided there and then to spend the rest of my life on working on this alternative aspect of AI. So I started doing that, as it happens, on January 1, 2001. I had basically, before Christmas, I had quit my job, and I had been thinking all Christmas weekend about stuff, and I basically started working on this as a real project January 1, 2001. I incorporated my company Synthi & Sync in 2004. I worked for Google for a few years. I worked for a couple of other companies, but on the whole, I have easily spent 20 years on these ideas and this project. And what I have been doing at one end, what I've been doing is basically creating theories for how intelligence works. But then I have been doing something like very few people are in a position to do, which is I've used my programming skill to program up large language models starting in 2001. So I have basically created 23 major large language models in 2001, only 2 of which worked. And so that's basically the experience that I have gathered. And I've been working on the second one of those for the past 4 years now, 5 years almost, trying to improve it to the point where the other language models are. And it's likely doable, and it's likely going to be a big deal. But at the moment, I don't have it. So I can use the other aspect of what I do, and that is basically an outreach, an educational outreach, try to get people to understand this enormous difference that we underwent in AI and to understand what it means for everything that they believe about AI. It includes what you should, how hard it should be, how expensive it should be, what should be done first, etc. How important is the corpus? How important is it to have a robot, etc. These are all questions that people are easily misled by the 20th century views of artificial intelligence, and setting them straight should be a priority. And that's why I basically am doing my outreach, because I want people to focus on that which works. Now, fortunately, a lot of people are focusing on deep neural networks and transformers and so on, and these things do work. So I'm not dissing them. I'm just saying they're doing it wrong. It could be done better. It could be done easier if you followed my theories. And so we can talk about in which aspects that is true and what matters the most in this thing. So my main discussion, to bring it to a conclusion, is basically that there's two kinds of problem-solving methods in the world, and people have always been used one of them. But some people have been taught to use the other one. And now they get confused when they are told to use the first one. And so this is the problem in a nutshell. And the two methods are called the reductionist stance and the holistic stance. And we can talk about that a lot.
Very good. That, I mean, when I thought of it, you have taught this stance forever. And there's this total moment where I saw the things that you predicted just like coming true. And then on a plane, I was listening to a Sam Altman speech from before ChatGPT, and I had just listened to it, and I got a text from you like, Sam, I believe everything Sam Altman says. And I'm reading it, having been trained by you, and I'm like, Sam Altman is making sense. Right. And I made sense of it with what you had taught me, and then I get this immediate text loop, and I'm like, okay, that's super ultra helpful. And so, do you want to lay out this kind of philosophical approach between reductionism and holism? Because that is where you started me.
Right. There is, if you go to the Stanford Encyclopedia of Philosophy, for instance, you can find about a half a dozen different definitions for the term reductionism. And they vary a lot, and some go back to the Greeks, to people like Anaximander. But what they have in common is that they are all describing various simplifications of the world. And in so doing, they do things like, okay, let's switch it to a different problem domain. Like if we have a gas, we can switch it to Newtonian mechanics by basically treating gas molecules as balls that can collide with each other. So these are basically domain-to-domain reductions. There is all kinds of other reductive ideas that they have, but in general, it comes down to basically building models of the problem. You basically, somebody with some sense, like a scientist or an engineer, looks at the problem situation, decides what matters, and they find a formula or equation. They may make it themselves, like Newton did, or they might take it from a book, like a lot of engineers. And then they they understand the problem well enough that they can apply this equation to their system, and they can get an answer, and then they can use this answer in the real world problem. And this has worked so well for 450 years. We went to the moon using this principle. We've done all kinds of cool stuff. But there's problems we couldn't do, such as protein folding. And then these neural networks come along, and they do protein folding like nobody's business. And that's because they are using the other problem-solving methods, the other problem-solving method. And so they come in two classes, and we can call them the scientific methods, which is the model-based one, the limited ones. They work 100% of the time, at least the simpler ones do, and they provide clear-cut answers. They also require perfect input data. And then the other set of problem-solving methods, which I call the riff-raff methods. They are the holistic methods, and they basically take sensory input and they learn from it, and they create patterns of patterns, building up experience, and they can't do anything until they have a problem that matches their experience. So the moment, if you build up a lot of experience over a lifetime, like an education, when you become an engineer and you got to build something like the Golden Gate Bridge, you know exactly in your education, you have been going through exactly what matters. You need to anchor these points. You have to measure the depth and so on. You have to do all of these computations, and you can do them because you're educated to do this. But the basis of being able to pick the right model is the understanding of the situation. And this is something that only comes from experience, and it cannot be explicitly taught. So let me, possibly I should tell the little story of Holly and her chocolates. And this story illustrates basically why we need to do something that is not scientific. We need to go beyond science. And I call it, I mean, Elon Musk and other people talk about first principles of science as the place where you have to start. If you have a serious problem, you have to bring it down to first principle science, because otherwise you can jump to conclusion and make mistakes higher up in your abstraction tree. And that could be detrimental to the end result. So they say, go to first principles. And that's how he describes his rockets and whatnot. I say that in artificial intelligence, that is not sufficient. You have to go one level deeper. You have to go to the 0th level, and the 0th level is the level of epistemology. And things that don't make sense at all in the scientific world suddenly start making a lot of sense in epistemology. And we find that if we're going to build artificial intelligence or even large language models, we have to understand this difference. We have to do it the way, basically, that the brain does it, and that is collecting experience. So the story is that imagine you're back in grammar school and you are in a math class and your teacher tells you the story, the following story problem. She says, Holly has 3 boxes of chocolates and there are 6 chocolates in each box. How many chocolates does Holly have? And somebody will say 18, and I say almost right, and somebody says 18 chocolates, and I say that's correct, because you have to add the unit to it, and that's something that's extremely important to an epistemologist, maybe not so for a grade school teacher. But basically, science is very good at answering questions like, how many chocolates does Holly have? You multiply 3 by 6, and you get 18 chocolates. But science is not very good at answering a whole bunch of other questions. A typical one is, how did you know you had to multiply? How did you know you had to multiply? If you can't answer this question with a straight face, and saying that you learned it in school doesn't count, because you didn't learn about Holly and her chocolate in school. You learned so many other things, but you didn't learn about Holly. The point is that in order to be able to solve these kinds of problems, you have to do an abstraction. And the abstraction is something that science cannot handle. They don't have equations for abstractions. They basically, when scientists doesn't extract an abstraction, they're solving an integral, and suddenly they figure out what substitution to make. They don't know how they did it. They don't have an equation for finding the substitution. There are such equations that Mathematica uses, but scientists, when they're basically solving an equation that looks like a sphere, I'm going to substitute mumble pi squared or whatever. And so that's their experience talking. That's their experience of solving thousands of math problems throughout their education that has led them to a position where they know when multiplication is the correct thing to do. And the answer to the question is, how do you know you must have to multiply? Is because you gathered enough experience to be able to pattern match the situation with Holly and her chocolates to a multiplication solution. And that is basically what reductionism is all about. That's the epistemic reduction, going from a rich world situation to a simple equation you can solve in a computer or a calculator, and then you can find the result 18, apply it back to the world and say 18 chocolates. Incidentally, the word apply is interesting because it means it's used in application in our iPhones. And that's exactly what we have. We have a computer-based model of a real-world problem in our iPhone. We enter some data and we get back a result. And the result is applied to the real world. That's what basically we call this application. It goes all the way back to the beginning of computing. So anyway, that's Holly and her chocolates, and basically explains why we have to go to epistemology in order to understand AI, because how can you figure out that you have to multiply or use any other problem-solving method for that matter if you don't have this context? And that's where we can go on with, you can ask questions or whatever.
Perfect. Let me see if I can summarize the Holly and her chocolates problem, right? So for so much of this, you have to walk along a thinking path, and that's hard for people. The reason we're recording this is so people can rewalk this thinking path. But I would say there's a sort of touchstone, which is, hey, you can figure out that if you want to know how many chocolates total in 3 boxes of a common unit, you can do that. But how do you know this operation set at all? How do you know the operation set, and how do you know which one to use?
Yes, I actually, normally I forgot to do it here, but I usually say Holly is 7 years old. I usually start with that. And then I say, and by the way, why doesn't 7 occur in your multiplication? Because it doesn't matter. How do you know it doesn't matter? Because experience tells me so.
Yeah.
You see how this, basically, epistemic reduction is discarding the irrelevant. And discarding Holly's age is extremely important as irrelevant.
It's Wednesday, April 17th, 2024, and you're listening to the PHX App Dev podcast. And we're talking with Monica Anderson today. Monica, when we left, you said, a magic pointer to something that you taught me a long time ago, which is reductionism discards context as a nuisance. And that, I mean, to me, that's the best lead into holism there is. So, can you tell us more about that and how you think about it?
Yes, consider something as simple as the equation F equals ma, which is Newton's second law. That is a very simple equation. And you have to basically, if you're looking at the problem, such as you want to estimate how good are the brakes in your car. Did you know that you can estimate the power of brakes in horsepower? It's basically completely equivalent to accelerating a car. You can just brake it. So you run the car up to 40 miles an hour and you shoot it with a video camera, you hit the brakes, you see how long it takes for it to decelerate, and now you can plug it into the formula. You can say how many horsepower your brakes are. So that's a typical way of solving a reductionist problem. Now, we didn't take into account the wind resistance. We didn't take into account the rolling resistance. We were just interested in the brake, but all of these other things also decelerate the car. And the engineer that's looking at this problem, trying to do it using this method, had to decide whether the rolling resistance and wind resistance should be included in the model or not. And they can include them, and there's formulas for this, but it complicates the model. It might not be right in an educational situation. So they go with F equals ma, and they're happy with the result. It's going to be correct within a % or 2, and that's typically good enough for engineers. So the question of what to include and what to exclude is crucial when you're doing a reduction to something that is scientific, and a model, an equation, etc. We'll get back to how you solve problems without doing these things. But we can look at what disappears when you're doing this thing, and it becomes increasingly annoying and increasingly embarrassing for reductionists to deal with more and more complicated problems. They try to predict the stock market. They can't keep track of all the variables. They try to predict things like intelligence based on race, and you know where this is going, and they get criticized for doing these kinds of things. And they don't, they look at intelligence as a result of where you live, and they don't take all the factors into account because they reduce them away as irrelevant too early. And now the results are controversial, and people can point at the discards as important things that they should have included. And so this is the problem with reductionism, is that there is a scientist always that has a model of the problem and of the world in their head, and they are the one dictating which equations to use. And this can be incorrect, it can be correct. When it's correct, it's fine. And surprisingly, in places like rocket science, these equations are simpler than they are on the street, because there's no friction in space, for instance. So it depends a lot about which domain you're in. But the moment you step into life, the moment you go from physics and mechanics and basic chemistry, you go to biochemistry, you go to medicine, you go to biology, you go to psychology, you go to ecology. The moment you step the border of that which is living, you're basically on the other side of a complexity barrier that is enormous. And the reductionist methods, they fail in everything that has to do with life. And this was discovered, this was debated, and by no other than Erwin Schrödinger, of Schrödinger's equations. Back in 1947 or 8, I think, in a paper called What is Life, where he basically, the first 80% of the paper, he discusses how difficult it is to take anything in the living domain and create physical models for them, and scientific models for them. And in the last few percent of the book, he goes on and takes back a lot of that. And I wonder if that is a pressure from somebody else, because otherwise the paper would have been too radical. This is something we've seen again and again. For instance, yeah. But the net of this is that is that we can recognize in general that life is the hard barrier to where physics basically can't do anything. And beyond that, we rely on the holistic methods. Protein folding is currently a shining example of that. But even before that, we use Shatter-Scott genetics, which is a semi-holistic method for doing gene analysis. And basically shooting at the genome, picking pieces at random, and then assembling them from the pieces. And that's something a reductionist would never do because it doesn't guarantee a correct result. But hey, it works really well for the genomic domain because there's no alternatives to it. In general, we use reductionist methods whenever we can. If you have a working model that gives you good results, you would be a fool to stop using it. But including going to AI, because they are holistic. We're going to get back to that a lot. They are basically working in the other domain. But the scientific methods, they are always dependent on there being somebody else doing the epistemic reduction and throwing away the irrelevant. And it typically is the scientist who creates the equation or the engineer who uses it.
Okay. Yeah, that's great. And I think the update of biological life is that's new in the teaching. And so that's real. That makes a super clear line in it, and that snaps lots of stuff into place. Okay, well, this discussion is nominally about why this works. And so given this background in reductionism and holism, why in the world does AI quote unquote work? And let's try to refine that definition. It starts to work in the biological domain.
Mm-hmm.
So big top question, why does it work? And then how is the example of the biological domain show it working?
It is significant that some of the things that work in biology, such as evolution in natural between species, etc., Darwinian evolution, is frowned upon by everybody in science. Some people say evolution is a scientific principle. Turns out that they're wrong. It's actually an epistemological principle. It's not at the level of science. It has to go below, because science doesn't have equations for evolution. But epistemology explains how it works. And it also explains how intelligence works. And the similarities are striking. One would think that basically once we can establish, you can basically make a short epistemological argument that says whenever you have these conditions for evolution, such as a competition for survival and a pattern that can propagate with some chance of error, when you have those situations, you basically have an evolutionary situation. And that can happen in many, many places. It can happen, I think it can happen in cosmology, but definitely can happen in real life. It can happen in certain, I mean, I don't know, even chemical fraction distillation sounds to me like something that almost evolves. So there's all kinds of examples of these kinds of things in life, but evolution between species is the number one example of something that is really powerful, and because it has brought out all the life on the planet, an enormous variation. The creativity of evolution is powerful, and we can get back to how basically computers can harness that creativity for themselves, and how we harness the same methods, the same algorithms for creativity as evolution does. Anyways, back to the disdain for evolution among reductionists, because it isn't reliable. It doesn't provide you an explanation. It has all kinds of problems, and it requires large populations. It costs a lot of effort to do it. They prefer to just be able to pinpoint the equation and get the answer. Point is that nature in the beginning didn't have these scientists, so it had to basically make do what it had, and it basically nature discovered by evolution. It basically discovered how to get better at it, and the one way to get better at evolution is to be able to evolve ideas in your mind, in your head. And so nature discovered intelligence as a competition between ideas in the mind. And this is called the neural Darwinism idea. It also can generalize to something called selectionism, which is basically the idea that evolution works all over the world. For instance, the cars we can buy are the cars that are made because we have selected those cars, and similar cars in the past. And so even the cars we can drive is the result of a selection evolutionary process. And so understanding that in the brain we have an evolutionary process that makes ideas compete with each other, and they breed with the best ideas get to breed with each other and generate even better ideas. That is extremely important to me. I've been following that trend for 30 years, that idea for 30 years, and Still nobody notices it. To me, it's obvious that that's how the brain works, because that's a kind of simple algorithm that evolution could come up with. Evolution cannot come up with stochastic gradient descent. It can't even come up with floating point. There's no floating point in our brains. So clearly, the approaches that we have been taken in deep neural networks and in transformers and in LLMs, they can be improved upon by going to something that is closer to that which is epistemologically necessary. And that is basically a system that ties concepts to each other through correlations, relations, synapses, and that uses Darwinistic evolution to throw out the bad stuff, the bad ideas over time, and just breed the good ones. And these are key ideas in epistemology, the key ideas for my system, but you don't really see them explicitly mentioned in large language models. I have this feeling that large language models are doing these things by luck and not by somebody understanding the problem and designing it.
Okay. Well, so maybe we need a specific definition of epistemology here. You know, if there's someone who's not familiar with all of this, then what kind of handle can you give people on just the concept of epistemology?
So if you can make a quick sketch of philosophy at the bottom, and then we build science on top of philosophy. But there's a few, now I can use my whiteboard. So there's a few interesting details about that. So if suppose this is philosophy, you can see this.
I see it. I got it. The writing is hard to pick up, but
okay. But this is philosophy. I'll write bigger. Yep. And then at the top of philosophy here is a layer which we can call epistemology. And the epistemology layer, it talks about things like truth and falsehood, about understanding, learning, about reasoning, about logic. All of these things can be defined at the epistemology level. They are born out of philosophy. And you can see why it takes basically a bunch of Greeks to come up with the good stuff here. And that's what happens. But then on top of this, we take some methods that we like, and we build basically what is the science on top of epistemology like that. And these are the reductionist methods. These are equations and other models, equations, formulas, hypotheses, theories, and they are all basically reductions of the world, the simplifications of the real world, but they work every time pretty much, and they require perfect input data. When you have a situation that doesn't match that, when you can't use these equations, for instance, in the case of understanding language, which is not reducible, understanding protein folding, it's not reducible. In these situations, you're basically stuck with using all kinds of stuff on the right here. The rest of the problem-solving methods, they are varying quality. Some of them are very good, some of them are very fast, some of them are completely useless in most situations. But we can call these the riff-raff methods. They are the holistic methods. This is what people use for millions of years since we were insects. And basically, we learn things and we solve problems by pattern matching. And only in around 1550 to 1650, we get the brilliant idea of gathering all the reductionist models in the book and calling that science. But we still have to do it. The way to get to one of these reductionist equations is that you have to use your brain using nothing but these riff-raff methods to form your understanding of the problem domain. And until you have that understanding, until you build all the crosslinks between the correlations that you need to solve problems in this domain, you can't even use science. So this comes after scientific education, after having studied the topic. These methods you can just use immediately. I think of the difference sometimes between reductionism and holism as the difference between plan it and do it. If you need to plan it, it's reductionism. Is you can just do it right away, it's holism. Language understanding is holistic, etc. Taking a step forward is holistic. You can't sequence your leg muscle by an algorithm because you don't even know what leg muscles you have. So basically, most of the time, 99.999% of the time, we're using nothing but holistic methods in our daily life. Even if you're a scientist, you're using nothing but these methods. It's using nothing but experience and your brain at lower levels of understanding. And only when you're writing a paper in science do you have to, or trying to solve a problem using basically bridge building after you have to use those methods, and they do require this understanding before you can even touch them. So this is the difference the thing that I'm addressing mostly, and that becomes important because AI actually lives in this right-hand side. AI doesn't live inside of science, which is the biggest surprise to many people. I'm saying AI uses these methods, and because they're using riffraff methods, they're going to sometimes give us riffraff answers, and people have started noticing that LLMs lie to you a lot. And that's just a matter of how many methods they can, how much information they have, how many methods they control. And putting these things in there doesn't help this. Trying to make AI scientific by putting in equation solving systems in them doesn't necessarily improve the understanding of the problem that they have. So it may not be that helpful. But these are the kinds of issues that epistemology can help you discuss in the AI domain in the same manner, if you will.
Awesome. Okay. Is that enough background to start answering the question, why does it work?
Yes, it works because it's the principle of gathering information, creating patterns that you can search, and matching those patterns to problems in the real world is something that is so simple that evolution, that nature could discover it. And science took human intelligence and hundreds of years to discover. So these are much more important methods than the scientific ones. And now that we have AI working on the right-hand side of the equation, AIs are actually understanding the problems. We may not need as much science going forward. We may not need much science going forward. We're going to basically ask our AIs, and they're going to come up with an answer like that, and it's going to be correct often enough that we don't have to double check using science. And that's a very different world.
Yeah, that's certainly, I never had this point of view that I really like Stephen Wolfram, right? And his focus is what is computationally reducible, and that's all the stuff in the science box, and what is not computationally reducible, and that's all the riffraff. But it is now computationally reducible to find the pattern to build riffraff models. Right?
Yes, I mean, you notice that it's very expensive to build a large language model because you have to gather enough of this stuff to have something to throw at every problem you can encounter. You have to have seen everything before in some way, shape, or form at least, and have enough abstractive capability to be able to do it. It's a tricky question.
Let's drop down the rabbit hole. Let's just answer the most basic question. How in the world, even if you have a lot of data, do you link all that? This is the how, the why it works. What are we doing with a machine? Because there's clearly a reductionist machine involved here. They can still only work on zeros and ones. Why does this thing work?
So the basic problem of AI is one of discovering abstractions. You have basically a situation with all kinds of data. You could basically take the bridge building example. You have all the numbers for the whatever. You got to understand what kind of abstraction makes sense. And so discovering the correct abstractions, the correct models, actually, I shouldn't say that because in everyday life, we're happy to discover an abstraction a little bit higher up. We don't have to go all the way up to the real models to solve something scientifically. We can go quarter way up and solve problems using whatever we have. And this is easy to explain in a physical skill context. Suppose you're learning to go ski downhill. Well, if you can't have a friend tell you how to ski downhill over the phone. That doesn't work. You can't be taught how to ski over the phone. So you have to basically do it yourself. You have to experience it. You have to basically fall down enough so that you have enough responses to your balance shifting and your ski sketching, etc. All of these little things. And all of these things have to happen fast. And if you have to experience something and analyze and think about it, you have spent 500 milliseconds. This is known as the Libet delay. You're living half a second in the past. This is not known to most people, but basically after you see something happening, there's a half a second delay before you get conscious of it. And you can find out that this is the case because, I mean, for instance, I open my bathroom cabinet and a lipstick falls out. I can catch it before I even notice that it fell. And that's like 200 milliseconds of fall. But if you're playing tennis, the first time you try to compute where the ball is, and it's always behind you, so to speak. So you have to get to the point where you can answer, not going all the way to the top and going down to the bottom again. You get basically this shortcut that goes from sensory input to physical output. Okay, hit the ball there, hit the ball there. you basically get there only by practice. Practice is exactly what you need. Here's a key difference between the methods in the box and the methods outside of the box. These guys get better with practice. Those don't. Anything scientific gives you the same answer every time. Anything holistic gives you better answer as it learns more. And the question is, which one do you want? Well, it depends on the application.
Okay. We're still circling the why does it work? So you have to do iterations. Why do these systems allow iterations to pay off? What are they doing at the bottom?
They're learning a little bit every time. And here is a basic rule of epistemology, is that you can only learn that which you already almost know. Learning a new fact or a new skill or a new input or even a new correlation, it means it's a creative task, because you have to fit it in the right place in the existing world model. And this takes a lot of effort to get it right, and we have algorithms for that.
Great. All right, Monica. So we're circling the question of why does it work? And you suggest that the transformer case makes a really good example here.
Mm-hmm. Yes, I mean, the function of the brain is, I have this saying that says, about theories of the brain, that says, the story of what the brain has to do is much shorter than the story of what the brain does. The brain carries an enormous amount of evolutionary baggage, including things like microcolumns and long-term things and hippocampus and all kinds of other stuff, and temporal, whatever, different regions in the brain, and they have evolved over time from previous species, etc., etc. So it's hard to make sense of everything. So going to epistemology is one way that you can see the pure problems. And the pure problems are basically the problem of reduction, of discovering an abstraction. For instance, one reason to know what's abstraction is that you can tell whether something is important or not. If it's a completely new thing, you may want to learn it. And if it's not, then you always just another one of those. You don't have to explicitly learn it. So what you learn, how much to crank up the learning in your large language model, are basically things that can be controlled directly by looking at these things. So large language models, they basically they are gathering experience, and the way that their experience works is that they discover correlations between these different phenomena that it's experiencing. I mean, in the simple case of language, we must discover patterns of words, etc., and we must rediscover them when we see them again. I mean, basically 90% of cognition is recognition, and so they have to recognize everything that they have seen before, and that requires that they have some kind of a data structure where you can take concepts that you have read about and compare them to other concepts that you have read about. And this is what large language models are using. Currently they're using a 20,000 dimensional space. There's basically 20,000 floating point vectors with there's floating point vectors in 20,000 entries. And they live inside of a graphics processing unit because they have to do computations on that. And the computation they want to do is, you can think of this word, if you will, start with words. Words basically occupy spaces in this 20,000 dimensional space. And two words are related to each other, like cat and kitten could be related to each other. And the difference, basically, dog is much further out than cat and kitten are. So the distance in this space is what determines how close something is to something else. And now you can take a bunch of items in this space and wrap a bubble about it and say, this is everything that matters about a cat. And you don't have a cat neuron, but you do have a bunch of neurons, if you will, or floating point numbers in the case of LLMs, that basically embody the concept of a cat. And whenever we talk about a cat in any aspect of this, you get some points lighting up in this space. So the ability, the power of this structure is how well can you determine whether two items are related or not? How well can you create a reification, a physical or a mathematical construct that says this is a cat in our system. If it lands in this bubble, we have a cat. And that can basically be done at that point. That can be done completely mechanically as long as you have this vector table. It takes a word and it gives you this vector in this concept space. And 22,000 floating point number is a very large space. There's basically difference between cat and kitten might be a difference in 20 dimensions of 0.6 or something like that, but most of them are going to be the same. And the reason that most of these dimensions are the same, have the same values, means that cat and kitten are close to each other, and they might differ in size or some other stupid dimension.
Yeah, let me get that relationship straight. So it's a 20,000 dimension space.
Yes.
And a cat and kitten might really encompass 20 of those dimensions. So
no, they encompass all of them. You have to specify every single one of those 20 for every single point in this space. So that takes a whole vector to say cat. It takes a whole vector to say kitten. And they are close to each other in some number of those, in most of those dimensions, but not in all. And it's a transformation from word to a point in a semantic space, which is the trick of the LLM. How can they do this? How do they come up with this magic vector? That's the big trick, and it predates LLMs by a few years. And you may have heard of this. This is basically called word2vec, and word2vec is the idea that you can read a bunch of text, even one word or a large fraction of text. And when you're doing that, you're navigating this 20,000 dimensional space to a point, and when you read the whole sentence, you are at the point in the space, and this is the space what the sentence was about. It's not just the word cat. This is what the entire sentence is about. And the system works basically. The whole learning process allows you to do this, and it basically embeds all of the syntax and other things that language has, which is not necessarily for analyzing it, but it basically all of these things become part of this cloud of points that the system can handle. And you give a sentence, you end up in a space in this, and you can immediately see what's around it. And if you're, for instance, if you're building a spam filter, you enter a bunch of spam, and they all end up on a cluster over here, and then you enter in a message, and if it's the clusters in that cluster, then you have a spam thing. So it's very straightforward once you have this vector. Where does the vector come from? This is a beautiful story. So word2vec, you can recognize that we're talking about word2vec because everybody uses this wonderful example of king minus man plus woman equals queen. So that's basically how you can navigate this. If king, queen, man, and woman are vectors in this space, it turns out that you can do this vector arithmetic, which reductionists like a lot, to navigate concepts in the concept space. And this was why they went down this route the moment they discovered it. But basically, how do you discover that, for instance, cat and kitten are similar? Well, you can read bunches and bunches of text, and we talk about more text than what actually goes into the learning of large language models, at least in the early cases. But you take a whole bunch of text, and the best models currently, I think, are done by Google. Maybe there's something elsewhere, but they read all this text, and they go through 5 words. They take 5 words, and first, second, third, fourth, fifth, and then they take the word in the middle, and they bury it. So basically, you find in the text, you say, feed the cat before leaving. And you see in another place, you say, feed the kitten before leaving, feed the dog before leaving. You can cluster all of the things that you feed before leaving into a category, into words that mean roughly the same thing. They are not the same thing. They are slot fillers for the same expression. But that's good enough for a lot of stuff. And this is basically how you discover the abstraction of pet from just these kinds of sentences. We have a category, we may not even have a name for it, but the system can discover the concept of petness by just discovering how we treat our various dogs and rabbits and cats and whatever. And so that's how word2vec gives us the abstraction, the semantics of words, the semantics of sentences. And deep learning discovered this, started using this, and then transformers started using this in spades. And that's basically the foundation of everything we have in natural language today. Like natural language understanding and NLU is based on the ability to take a word2vec vector called an embedding, and then use that for learning other stuff around it, and increase the power of the embedding in the current sentence by refining it and so on. These are kinds of mathematical operations that we can do in this situation. But the word2vec trick is the one that made this possible.
Okay. So I realize asking this question of like, why does it work? We're back to riffraff methods and holism here. Like, okay, given what you have taught me, like I just look at, first of all, the machine essentially is going to break anything it gets into, a kind of Madlib. This is my rudimentary thing. Is that,
I love your Madlib experience. Madlib to me is basically these little words that you put on your fridge door and you can move them around. You can imagine as machine learning of language as being throwing them on the fridge door in random order, and whenever you read something that's close to something that's related, you nudge them quarter inch closer to each other. And you keep doing this for a year with every piece of news item that you find. And over time, you will find that cat and kitten are very close to each other. And this is basically machine learning on a fridge door. I never thought of this before, but this is a lovely metaphor.
Nice. Well, great. There we go. Here's my reductionist question. How do you do one?
Yeah.
And so with the Madlib fridge door thing, that you would get like some phrase that pops up on a screen, and cat and kitten have occurred more closely in your own mind. Your mind will sort of make these connections.
The easiest algorithms basically say words that are next to each other will get close to each other in the graph. And this is a well-known equation, and you can do it mathematically, and then it's called the Viterbi algorithm. It basically uses Bayesian learning to do the same thing. It's not strong enough to be used for language understanding because it discards too much of the context, but it's basically the same idea. You basically learn to move things towards each other as you encounter them in pairs and triplets and whatnot.
Perfect. All right, well, let's roll off from there. I think this gives the audience like a super great landing spot, and maybe why don't you do a teeny summary here, and then maybe even offer us what next idea we should learn, and maybe we'll pick that up for the next one.
Certainly. Yes, the summary is that humans use one way of solving problems for millions of years, and then science came along for 400 years and found a better way. And now it's run its course, and we have to go back to doing it the first way. And therefore, the 21st century is going to be revenge of the whole. This is going to be revenge of methods that do it rather than plan it. And we're going to see it at all kinds of levels even inside of science. We're going to do more things like protein folding, which is a scientific problem, but science can't solve it. We're going to do more of those using artificial intelligences and other holistic methods to jump to conclusions on scant evidence.
Awesome. So great, Monica. It's fantastic. Okay, what is the next concept we should be thinking about and that we'll talk about next?
We can think about this. I'll give you as a homework for next time. How do you know if something is important?
Salience, relevance, realization, right?
Yes.
Salience.
How do you know that something is important? This is a significantly important question in AI.
All right.
And we have good answers, but you may not think of them unless you have a holistic mind.
Okay, salience is next. All right. This is the PHX App Dev podcast. It's Wednesday, April 17th, 2024. And we've been talking in the first of a series to Monica Anderson about how to build your intuition about artificial intelligence. Monica, as always, thank you so much. And we will talk to you next time.
I enjoy sharing this. Thank you very much.